So we are still in chapter 5, and we are evaluating atmospheric stability based on our observations, like pilots do, and based on the data. We've already talked about force lift. Now we're going to talk about how our observations fit into some funky data on the sounding, specifically on the Stuve sounding. So when we look into this Stuve sounding, we may observe outside that we see fog, and we see a thin layer of fog, or maybe we see a slightly thicker layer of fog there. But either way, we observe a fog layer outside. When we look to the Stuve sounding for the data, we see this strange direction. Everything had been losing warmth at altitude. But suddenly now, in this area, we are gaining warmth at altitude. We're going up in altitude, and our temperature is going up as well. That was after the forced lift that we saw, which was probably from convection in this area. So you can see, you already know about fog, and you know that this looks like a dawn. And so probably this ground conducted its emissions to the first few inches, and then the atmosphere wanted to force lift that with convection, but it's finding that there's very little movement in the atmosphere, that you've got a stable atmosphere here because something is pushing down on that, another competing air mass. In the same way here, this roadway emitted out very well overnight, and as a result you've got this fog a bit higher in this area. This area cooled here, met the dew point, and formed a fog. So you know that this was probably due to radiational cooling and conduction and convection in this area for the forced lift. If you go and actually do the calculations of the data here, you see that you are subtracting your initial temperature from a later temperature. And in this case, the initial temperature was around 18 degrees Celsius. Here's 10 degrees Celsius, 20 degrees Celsius, around 18 degrees Celsius. And your later temperature was at around 24 degrees Celsius. And when we look at that, we subtract 18 minus 24, and we get a lapse rate of -6, a negative lapse rate. I know that this sounds strange to you from your work on geometry, and meteorology does have a strange slope setup here because we are looking at the change in temperature, the x-axis here, over the change in altitude, the y-axis. Normally that is flipped, but in here in meteorology we look at lapse rates rather than slopes, and we calculate our lapse rates as initial temperature at lower altitude minus later temperature at higher altitude. 18 degrees minus 24 for a negative lapse rate that increases in temperature with altitude. And that negative lapse rate on calculation is associated with the stable atmosphere that we observed. So we observed something, we collected data, we applied math to the data. That's the trajectory that we look at in science. We make an observation, we look for data, we try to apply mathematics to the data in data analysis. When we look at this, we can note that negative lapse rates that move to increase temperature with altitude, are known as inversions. This is known as a radiative inversion because that stable atmosphere was due to warmth that was moving up in the atmosphere, but it has a lid on it from a competing air mass. We're going to talk about that soon. When we look at how this looks to a pilot and this lid, we see in here that he is in a very hazy, smoggy, or she is in a very hazy or smoggy environment that they're flying in. And in fact, we note here that the temperature is increasing as you go up in altitude. And that is shown on the data as an increase in temperature as you move up in altitude. Here's the graphical representation of that inversion, much like the Stuve diagram that we saw. And this temperature will continue to rise in this area until it meets this competing air mass, which is above it and is more dense. Where the temperatures meet, you have a lid that seals this air from the ground in this layer, and the cooler layer, the more dense layer, is above it. So this is the lid where those temperatures meet and the top of the inversion. Above it, you will have more dense and clear air. This is Los Angeles here and their famous smog. When we look into another type of stable atmosphere, we may observe this, a thicker fog layer. In other words, this man is on the top of a mountainside looking down on a very thick layer of clouds. You can generally see through smog. In this area, you can't see through these clouds. This is a thick fog layer. And we can observe this, and we can also look for data that shows this. The data would show a straight up and down line for the environmental lapse rate on the sounding. So in other words, you had an area here with a forced lift that brought the water vapor up through the atmosphere. Then you had an area where there was a bit of a drop in temperature, not a large drop in temperature over altitude, but enough so that a cloud could develop and it could rise. In this area, you have temperature that stopped dropping. And when the temperature stopped dropping, this water vapor couldn't be warmer than the temperature above it that had stopped dropping in the atmosphere, in the environment. So this is known as an isothermal environmental lapse rate. Isothermal meaning same, iso, like in equivalence, like isometric exercises, you're moving the same amount. Isothermal, the same temperature. So as we go up in altitude, the environment or the air maintains the same temperature. Why would this happen? We'll get into that in a second, but it does put a lid on thicker clouds that have condensed in an atmosphere that allowed for a bit of a rise. We look at the average movement of this stable atmosphere as being very close to zero. There was some movement upward here, and there is a downdraft near here, but once you get into the isothermal area, you're very close to zero for the movement of this stable atmosphere. This tends to be another stagnant atmosphere, and you can think of it as looking for data that shows environmental lapse rates that stand up straight. So stand up straight lapse rate is associated with stagnant atmospheres and stable atmospheres. So I hope that those mnemonics will help you to think about how the lapse rate looks for a stable atmosphere. The lapse rate can look inverted, it can look straight, it can look just a bit tilted off to its regular lapse direction. When we look at the data that we have for this particular sounding, we see basically an isothermal area. It's not perfect, and most of science is not perfect, but here was an inverted lapse rate. Here is closer to an isothermal lapse rate. Yes, it goes back and forth a bit, but over the course of 1,000 meters here, between 500 meters and 1,500 meters, you are at the same temperature, right at about 24 degrees Celsius. Overnight, the atmosphere can make itself more stable, and it does that by looking at cooling at the ground level and emissions. Those are the observations that you make overnight, and warming aloft from those emissions, and that impacts our data. We see our data on the sounding, and we see this average environmental lapse rate, which has for the lack of a better word, a slope that approximates this angle. But we start to cool at the ground and move the temperature down, and we start to warm aloft and move the temperature up, and that moves closer to an isothermal lapse rate, or maybe a temperature inverted lapse rate that would be associated with fog or smog. This would be associated with a big cloud bank generally, and this could be associated with fog or smog. So overnight, the atmosphere can make itself more stable by cooling at the ground and emitting up to the air and warming the air aloft. Now, in terms of how this looks when we look at a graphical representation of many different types of lapse rates, these lapse rates for stable atmospheres are going to be either inverted or isothermal, or have just a bit of a lapse, and that is associated with stable environments. Next up, we're going to be talking about lapses that are a little bit more angled in conditionally unstable environments, which are very different. They tend to be the fair weather cumulus that you see. You've got updrafts in the cumulus clouds. You've got beautiful downdrafts in the blue sky. So all here, this is a very conditionally unstable, healthy, average atmosphere where you have updrafts in the cumulus clouds and downdrafts all around the cumulus clouds, revealing blue sky. Back here is our last set of videos on unstable atmospheres, but we'll get to that.